discuss? I gave you this problem in the previous lecture that if you have a multiplier A is a 13, a modulo function is 64, you will choose, and C is 0 increment, and the value of seed you will have 1, 2, 3, and 4 by this linear conjuncts. The formula is, or recurrence relation is, xi plus 1 is congruent to A xi plus C mod m. Using this, I have told you to develop what will be the period of certain different values for seed. So anyone have done this?
Yes, sir.
Yes, sir.
Yes, sir.
Very good.
Yes.
What is,
Yes, sir.
what will be the period for x0 equal to 1? If you can consider, then what will be the period for this? What is P?
16.
16.
16, sir.
Yeah. And in the previous, the next page, I already have that values. You can just check for your answers. Okay. If so, you can just observe that for this is x is equal to 1 value. This is for x is equal to 1. This is for x is equal to 2. This is for x is equal to 3 and 4. This is for 4. And you can just observe that for x is equal to 1, the period is 16. X is equal to 3 is also period is 16. For x is equal to 2, the period is 8. And for this one, it is 4. So if you choose your different seed, the period of random numbers will be different. Okay, in that, and why it is so, that we have taken our A is 13 here. Our A is 13, which is actually in the form of 5 plus 8k, where k is equal to 1. So it is of the form 5 plus 8k, and your m is 2 raised to 6, which is 64. Okay, so the period is always m by 4, which is 16. For x0, if you choose is 1, and x0 if you choose 3, because it is then number if you choose, then you will have this thing according to the previous data which I have told you here. See, if n is of order, or f is m is of the form 2 raised to b and c is 0, then your period should be of the form m by 4 if x0 is an odd number. Okay, and your A is of the form 3 plus 8k or 5 plus 8k. So here we have did that actually. Your A is 13, M is this 2 raised to 6. So your period should be of the form 16 because this A is of the form 5 plus 8k. If your seed is an odd number, so here for the seed is odd, that is exactly of 16 cycle will be there. So this is just by checking what the theory says regarding the thing. And in the similar manner, I will give you this PDF which I have prepared for you guys regarding the different values and different cases which we have here discussed. That means if I consider this m as a prime number or it is a power of 10, what are the things you will have? So will not take much time to generate this random numbers, we directly go to the a test for random numbers. So my objective for now next few lectures is for testing your random numbers. When you generate a random numbers using this way, whether that random numbers are uniformly generated or they are independent. So we have a frequency test for that. In the frequency test, we have two tests we will going to study. The first one is called Kolmogorov-Srnimov test. Another one is chi-square test. Both this test, what is the objective of both this test? Is to test whether the given random numbers are uniformly generated or not. So both this test is used for uniformly generated test. And in short, this test we call it as AS test. The second one is autocorrelation test. This autocorrelation test is to test for correlation between the number and compare a simple correlation to the expected correlation to 0. So expectation that the correlation between the things will be 0. That we will do. So what will be the hypothesis for uniformity? When you will say that, or what will be the hypothesis for, so we can write down testing hypothesis, testing for uniformity. What is the hypothesis? Anyone?
Not uniform.
Hypothesis. The random numbers which we generate from Ri are what so on. That will be uniformly generated or not. What is u of 0, 1? That is uniformly generated number between 0 and 1. And h1 is Ri is not uniformly generated. This is the hypothesis. The null hypothesis h0 is read that the numbers are uniformly distributed on the interval 0 and 1. Failure to reject the null hypothesis means that evidence of non-uniformly has not been detected by this test. Whatever the test you are applying, whether you are applying KS test or this chi-square test, then this is the hypothesis we are following. That H0 is a null hypothesis when we are saying that the numbers are uniformly distributed, and it is rejected. That means it is not in the form of uniformly distributed numbers. The another one is the test for independency. Here we have using the hypothesis. The hypothesis is H0, if Ri is independent, and H1 is not independent. That means not independent. So this is the hypothesis we are following to test. And for each test, a level of significance. Everyone know about what do you mean by level of significance. Significance is there. So you are saying that when you have a probability distribution like normal distribution, which area you have to neglect. If you have this one, you will neglect this much. So this is the area you are neglecting. So you are expecting all the things is drop, means come into this. So it is called the level of significance. Okay, and that value usually denoted by alpha. So for each test, any of the test you are applying, the level of significance must be stated when you are starting. That means this how much area or how much percentage you want to accept that this is a uniformly distributed or not, or this is independent or not. How much percentage is there? So that value will denoted by alpha, or in generally they are in any of the test we are applying, it will denoted by alpha. The level A is a probability of rejecting the null hypothesis. When the null hypothesis is true, then this alpha is P is equal to reject H0, H0 is true versus H0. So it is conditional probability is there. So it is a probability of reject H0 and H0 is true. And the decision maker set the value of for any test frequency, the alpha is said to be 001 or 0.05. So these are the two values we generally take to fix this frequency distribution if it is there. Now there are frequency test is there, so we'll learn one by one each test regarding the each test. So as I told you, for the uniform distribution we will going to study about the two tests. The one of them is KS test, another one is chi-square test. So let me talk about the KS test. So I'm just considering the CDF, that is a distribution function, continuous distribution function, as f of x of the uniform distribution with imperial CDF Cn of x of n is the observation, is the number of or sample of observation you can consider. So by definition, this CF or f of x is x if it is between 0 and 1, and Sn of x is the number of R1, R2 up to Rn which are less than or equal to x upon n. So what is Sn of x? Is how many of this, the number R1, R2 up to Rn you produce which are less than or equal to x, and n is the number of sample. If n is a large, if you pick up n number of samples will be large, then you will get a better approximation to become a null hypothesis is true. the null hypothesis is true means we will accept that as a uniform convergence. And what do you mean by this imperial distribution? This imperial distribution is either a discrete or continuous form, and is the parameter that observe the value of in the simple data. And this is in the contrast to parametric distribution family, such as exponential, normal, or Poisson distribution, which characterized by specific a small number of parameters such as mean and variance. And this imperial distribution may be used when it is impossible or unnecessary to establish the random variable as any particular parameter distribution. And all sort of things is there. And I will explain this case algorithm while we solve the example. So I will take this example here. So this example I am considering, this is the example we have, that a customer at local restaurant arrived at the lunchtime in a group of 1 to 8 persons. The number of person per party in the last 300 group has been observed, and results are summarized in table 2. What is table 2? I'm just also writing in the next table. In the next slide, I will write that. So that is, we also can put it here. So this is the number of this arrive per party. That means number 8 groups are arrived, and total 300 groups has been observed, and the results summarized in table 2. That is, this is the result. This is the frequency. In the first group there is 30, second it is this, so frequency is there. This is a relative frequency. Everyone know what you mean by frequency and relative frequency, cumulative frequency? Yes?
Yes, sir.
Yes, sir.
Yeah. So this is a relative frequency is there. This is cumulative relative frequency is there. Okay. And again in the figure 2, so that also it is actually a histogram is given uh, versus number of party versus relative frequency. So that also I can show it to you. So this is the histogram is there. A number of parties is there and versus relative frequency, which provide the histogram of the data that we gather. In figure 3, it is the given a CDF for this data. What is CDF? That is the imperial CDF of the party size. That also I can show you. That is this. So this is the arrival party. That means in the first is cumulative frequency is there on this side, and then it will increase like this. Okay, it is increased to 1. So this is the imperial CDF of party size is there. So this is the example, and the CDF is given in the figure 4 called the imperial distribution of the given data. The figure 4 is will show you. This is the f function f is there and versus x, and this is the Imperial CDF to loss and repair of the time. Now here our objective is to dealing with whether it is a random process is or into the group which we arrived in this local restaurant. It is the uniformly distributed, peoples are uniformly distributed or not, that we need to check using this KS test. Now for that, what is KS test? We need to learn, and we need to see what are the steps to deal with. So I already have defined what is fx. So in the previously, what I have shown you, the fx is this Imperial CDF for the function, and Sn is the number of R1, R2 up to Rn which are less than or equal to x divided by n. So if you can fix your x and the number of observations are there, so this is the number of observations we have here, and based on this we can define one function that is called the D function, which is a maximum of this fx minus Sn of x. Fx is whatever the distribution theory says, this is the number of observations. Okay. Now the sampling of distribution D is known to you, and for the critical values of this one, you will, when we are talking in the examination point of view, it is given to you. So that means what should be the value of D is acceptable and what is the value of D is reject, that you can, that table is given to you, like in other test you are doing for in the statistics. Here it is the same thing. Now what is the steps? What are the steps? So step 1, I will do that also. So this is the steps we have to follow to discuss this method. So step 1 is to rank all the data from smallest to largest. That is the step, first thing you have to do. That means whenever you are generating a random number R1 to R2 up to Rn, then you have to rank them as smallest to largest. That is the step 1. The step 2 is to compute D plus. How to compute D plus is small I upon n minus Ri, where maximum of this value. Okay, D minus is Ri minus I minus 1 by n. Step 3 is to compute D, which is the maximum of D plus and D minus. And step 4 is you have to see the what is the critical value from the table, which is given into the back side of your book, or when you are dealing with the exam, it will be into the table book. So you have to see what is the critical value for that, and according to that you will decide. Here n is the number of sample size is there, and according to that you will decide whether you can reject your data or you will accept that data. And step number 5 is also there. So step 5 is saying that if the sample static D is greater than critical value, that is D alpha, which is D alpha is the table value, the null hypothesis of the data is uniformly distributed is rejected. And if it is less than, then we can say that it is except. So it is D is less than or equal to D alpha. Conclude that the no difference has been detected between the true distribution, this, and the uniform distribution. So it is accepted the things. So let us give. Let me have one example here. Let us suppose that there are 5 numbers are given to you. So that is R1 is 0.44, R2 is 0.81, R3 is 0.05, and R4 is 0.93. We apply this case algorithm or case test for this to test whether this is a uniformly distributed number or not. The alpha significant value is given 0.05. So the first step is to arrange this. So you can see that in the first step you have to rank them from smallest to largest. Okay. So the first thing will write down into the form of a smallest to largest. So the smallest number is 0.05. Then you will have 0.14. Okay, 0.14 I have not written. So 44, 81, that number is left. 0.14 and 0.05, this is 4 and this is 6. 3, 4, 5. 5 numbers are there. So this is the first thing, second number, then next number is 0.44. Then you will have, it is 0.81 and then it is 0.93. So this is your array. What is the next step? The next step is to compute D plus and D minus. To compute D plus, you require I upon N. And to compute D minus, you require I minus 1 upon N. So let us compute what is capital N here. In this case, what is capital N?
5.
5. The number of distribution. So it is I upon capital N. What will be the I upon capital N? This is R1, R2, R3, R4, R5 that we have. This number is now rearranged. Okay, so forgot about this. So we have rearranged that. This is the first number, this is the second number, third number, fourth number, and 5. So your I is 1, 2, 3, 4, 5 here. So this is 1 by 5. This is 2 by 5. This will be 3 by 5. This is 4 by 5, and this is 5 by 5. 5 by 5 is 1. 4 by 5 is 3 by 5 is 1 by 5 is 0.20. 2 by 5 is 20 upon
0.4, sir. 0.4.
0.4.
3 by 5 is
0.6.
0.8.
0.8.
1.
okay. Then the next step is to compute I upon N minus Ri. This is the thing which we have to compute. I upon N minus Ri. So that we will do 0.20 minus 0.05, which will be gives you 0.15. This is gives you 0.4 minus 0.14. That is 0.26. 60 minus 44. 60 minus 44 is 0.16. And 80 minus 81 is negative value. So we are not considering this. This is a negative value. 80 minus 81 is a negative. So we will not consider that. 1 minus 0.97. So it is 0.07. So this is the value of. So what is your D plus? The D plus from this previous quantity it gives you maximum of this value. So the maximum of this value will be 0.26. This is your D plus. Next is I. So previously I have to calculate I minus 1 by n. I minus 1 by n. So what is I minus 1 by n? Now I need answer from you guys. And then Ri minus I minus 1 by n. So here is 0 by 5. So this is 0. This is 1 by 5. So it is 0.20. This is 0.04. This will be 0.60. And this is 0.80. So it is Ri minus 0. Ri is this 0.05. 0.14 minus 20, which is a negative. So that's why we are not considering this. 0.44 minus 0.4. So it is 0.04. 0.81 minus 0.60. So it is 0.81. 0.93 minus 0.80. So it is 0.13. So we'll have D minus, which is the maximum of this value, which is 0.13. So we have calculated actually two things, D plus and D minus. Now we need to calculate what is the maximum of D plus and D minus, which is D.
सर 0.21 होगा ना वो
21 आएगा ना D minus.
D minus 21. Yes. This is 21. So this is D is maximum of D plus D minus, which will be 0.26. And now we'll see the table. So I will show you table also. See, this is, it's not visible correctly, but it is D0.1, D005, and D0.01. So what we got, we have given that alpha, you have to take your alpha is this 0.05 and your n is 5. So that is your degree of freedom is 5. So for n equal to 5, that you have to look at in this table, in this value. This value will give you for D25 is 0.565. So that is the value of this table value, that is called critical value. Tabular critical value is 0.565 and your observed value is 0.26. So what we can say, according to the step number 5, here we have D alpha is 0.565 and we have a D, which is, we calculated 0.26.
H naught will be accepted.
Accepted. So this is says that if D is less than or equal to D alpha, conclude that no difference has been detected between the true distribution of these random numbers. So this is known as KS algorithm, okay, or KS test. Can you able to make a programming for this test? That is one of the practical you have. One practical is making a program. Either you will do the program in R or in Python, whatever you like. But this is the steps, this is the procedure that you can take. So first what you have to do is you have to consider your number which is of the form increasing order. You have to put smallest to largest. Then you compute this d plus and d minus, and from that you will consider what is the maximum value, and then you use this table which is already available in R, and you compare that value with the observed value, that is this, and you can say that whether the generated random numbers are uniformly distributed or not using this test. So will you able to do the programming for this? Have you understood the test?
Yes, sir.
Yes, sir.
Okay. So
Yes, sir.
I don't think so. There is another example is needed to do the practice. If I give you another example, you are able to do that yourself. Yes, or you required another example. Then I will give you as an exercise. You can, even though in my lecture note, which I am sharing you uh, in Moodle or maybe on another platform, you will
Google
have
Class.
that is as a exercise. There are lots of other problems are there. You can just take. Yeah, what you are saying? Last person, I have not heard you. Okay, then we'll discuss the next test, which is the chi-square test, which also the objective of this test is also to test whether your data or whatever the number you generate is uniformly distributed or not. And a sample static for this chi-square test is denoted by this notation. Chi-square is equal to summation ironing from 1 to n OI minus EI square upon EI, where OI is the observed number and observed number in ith class, and EI is the expected number in ith class, or in general it's called the observed value minus expected value, its square upon expected value. What is the expected value? EI is capital N upon N, where capital N is the total number of observation and small n, actually small n minus 1 is number of classes, whatever the number of classes are there. So n is number of classes, capital N is the total number of observations are there. Let us solve this. Let us understand how or what is the work rule for this one, for this test, by an example. So I will give you this data to you. So this 100 numbers are there here. 100 is there, yeah, 3, 3, 5, yeah, and yeah, this is 100 numbers are there. So the first thing we have to convert here. Alpha is given as 0.05. That is a critical value. and we have to see in the table for chi-square test. We have to check whether this random numbers, 100 random numbers, are uniformly distributed or not. So for that, what we'll do, we'll take some sample interval. So we have to make intervals, and we have to drop down the each entry, how many entries are observed in that intervals. So well, let us fix the number of intervals will be 10. Small n is 10. And so the interval, and we can observe that all these numbers are between 0 and 1. So I need to divide this closed interval 0, 1 into 10 equal intervals. So hence we have the intervals are close 0 to open 1, close 0.01 to 0.2 up to 0.9 to 1. So this is the intervals will separate. And we can now let us, and you can count how many numbers are between in this intervals. So 0 to 0.1, how many values are observed? That is called the observed value. So let us do it for one. The rest of the 10 I have already data, but let us try to do for the first entry. How many data is between 0 to 0.1? So this is not there. So in the first, there is no data. In the second line, there is no data. The third line, 1, 2,
6,
3, 4,
6,
6,
5, 6, 7, 8. Yeah, so altogether 7 is there. Okay. Yeah, it is a 1, 2, 3, 4, 5, 6, 7. Yeah, anyone? Anything left? No. If I consider this 0.1 also in that, then it is 8. So that's why it is 8 data is there. So I am making this closed interval, this is open interval. This is open interval, and this is closed. Otherwise, one data is there, then it is left. So this is the things we have. So let us make a table of regarding this. So if there is interval, interval means one. First intervals I already talked to you. What is first interval is this, second interval is this, third interval, and this is the 10th interval. The interval is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And in the interval, you will have 8 observation. Here is 8, 10, 9, 12, 8, 10, 14, 10, and 11. So altogether it is 100. So what is this value is OI. What is EI? That is expected value. As per the, it is capital N upon small n. It is the expected value. Capital N is the number of observation. upon number of intervals. The small n is the number of intervals. So how many number of observations we have? 100. So it is 100 upon 10. The number of intervals are 10. So that's why it is 10. So all these values will be 10. It will not be changed. Next is OI minus EI, that you can calculate. That is 8 minus 10 minus 2. This is also minus 2. This is 0. This is 1 minus 1. This is 2 minus 2. 0, 4, 0, 1. Then OI minus EI square. It will be 4, 4, 0, 1, 4, 4, 0, 16, 0, 1. And then lastly it is OI minus EI square upon EI. That is this value upon 10. 0 0.4, 0 0.4, 0, 0 0.1, 0 0.4, 0 0.4, 0, 1.6, 0, 0 0.1. And if you sum all of them, it will be 3.4. So that will gives you chi-square is 3.4. And using this table, that is the chi-square table, let us gives you that also. So what is the degree of freedom here for the chi-square test? Anyone know? It is n minus 1, not n.
-1.
Yeah, it is a small n minus 1. So you have to see the table for 9 entry. It's running slow. Yeah. So this is the chi-square table. And what was our value of alpha we have fixed? 0.05. This was the value of alpha. So you have to check for nine entry 0.05. That value is this 16.9. This is a chi-square 0.05, and as your small n is 10, so it is n minus 1, so it will be 9. So ninth row here, and this as alpha is 0.05 is already given to you. So 16.9 is your chi-square, 0.059 is 16.9, and our observed value is 3.4, which is less than this. So will not reject the null hypothesis. Okay, so as per the things, this is also, this data is given to us. It is also as an uniformly distributed numbers.
Excuse me, sir.
Yes.
Sir, actually the table value is 16.9190. So can we round off it? Whole value, table value is 16.9190. Actually, I have statistical table, so.
Yeah, it is fine. If you can round off. Here, whatever the data I have, whatever the table I have, in that it is given 16.9. Yeah, it may, see, this is also computed value. So it is written here only in one decimal places. So you can take 2 decimal places, 3 decimal places. Depends on the accuracy, how much accuracy you need. Everything is computed from the that theoretical equation or your curve, and from that this data is there.
Yes, sir.
Yeah, you can take it round up, or you can take, if you want more accuracy, you can take it in more decimal places over there. Yeah, that's it for today. I think so. We have did enough things for today. So we have discussed in this lecture two things, two important KS test and the chi-square test, and both the tests are testing your random numbers when you generate a random numbers, whether they are uniformly generated or not. For the independency, we will discuss in the next lecture. Okay? What are the tests for the independency we will going to discuss? That we will discuss in the next lecture. Okay.